All right, we are starting Unit 9 with, we're going to start with electric current and resistance. So we're going to define what exactly current is. We're going to define what's called drift velocity, which winds up being the actual speed that the electrons move through a wire, and you'll be very surprised at how slow it actually is. And then we'll get into resistance, which is, well, pretty much what it sounds. It's a resistance to the flow of electrons. It's what keeps electrons from flowing as freely as they should. We'll define it in a really silly way, which is an impractical and boring way of defining resistance. And then we'll talk about the easy way, which is how we'll get into Ohm's law, which is how we govern resistance and current. Okay, so everything until now, guys, has been dealing with electrostatic conditions, where the charges don't move, or if they do move, they stop very soon. Like with a capacitor, the charge will move until the capacitor is charged, and then they're stopped again, and we have a static electric field, and we move on from there. Now we're going to talk about current, and current is the actual flow of charge through a wire. We're talking about the movement of charge itself. Okay, in fact, that is the actual definition of current. Current is the flow of charge. It can be thought of as, or what has always helped me think about it is it's the charge velocity. Okay, don't adhere too closely to this, however. It's not meters per second. Okay, it is think of it more as the rate of change. Okay, it is the rate of change of charge. All right. Yes, kind of. Okay, so imagine we're in a wire and we have this cross-sectional area here, and what charge is the how much of these charged particles are going through our cross-sectional area per unit time. Okay, so we have our, real quick, we're going to draw a, okay, so we have a really non-functional current because it's just a battery and a switch, and as soon as we turn the switch on, then the whole thing is going to heat up and probably melt because we don't have anything slowing down the electrons. But if we take any particular spot, it's how much charge is flowing through that place per given second. All right, and current is then, current then is charge over time. Okay, equals coulombs. Coulombs per second. Okay. Now think about this. We deal with things. Our electronic devices deal in things in coulombs per second. In fact, this actually has a unit. Let me go on with that. A coulomb per second is a C, 1 C per S, and one of these is called an ampere. Okay. After Simon Ampere is the guy's name, and I think he's got I think Simon's his middle name. I don't remember what the first name is. Okay, we don't call them amperes. We actually call them amps. Okay, unless you're French, in which case you insist on saying the entire name because he is a Frenchman and you want to give him the respect he deserves. The rest of us just call him amp. Okay, we call an amp, or the symbol is A. Okay, please make sure that you're not confusing this with area. It happens. Okay, and so current also has a volume. So current is given by I. All right, current is I, and it will equal our change in our charge over our change in time. Okay, and we do call this the amp. It's called an amp. All right, and yes, if we do this on the very tiny scale, this does become dq dt. All right, so it is the rate of change, the instantaneous rate of change of charge, is our current. Okay, so we're going to draw a wire. Okay, and this is actually a nifty, cool. I recently learned this technique to draw a wire. This is a cross section. There we go. Okay, it's a cross section wire. We kind of like take it like a potato chip cut out of both sides. Okay. All right. This is a wire. The wire itself is electrically neutral, but inside the wire we have our atoms of metal. Okay, they are probably not quite so neatly arranged. And around our atoms of metal, we have, we'll pretend this, we have the valence electrons. Okay, and hopefully you guys remember enough of your chemistry to remember what a valence electron is, particularly for a metal. Okay, these electrons are free to move within the metal. Okay, they are non-localized. They are not bound to their particular nucleus. Okay, this is the sea of electrons, if you remember from your Prentice Hall chemistry text. So, so these electrons are in here, somewhat randomly around their nuclei. Okay, and if we have a an electric field flowing, we flip the switch, and oh, by the way, this is why electricity happens so fast. It's not because the electrons are moving fast, it's the electric field is instantaneous. Or virtually, the electric field is pretty much at the speed of light, and so that's why you turn on the light switch and lights instantly turn on, is because the field traveling through the wire gets turned on. It is allowed to flow through the wire. And so we get our field, okay, flowing through the wire. Well, if this is the direction of our electric field, which direction is our electrons going to move? The opposite direction. They'll move back towards the positives, right? Okay, so our electrons are actually moving around. So we have an electron here, and this actually kind of goes a little something like this, where they move and they kind of bounce around, eventually working their way between all the atoms and moving back towards the origin of the electric field. Okay, now, but wait a second. This is a wire, right? Wires are made out of conducting materials, right? So isn't there no electric field in a conductor? Inside a conductor, there's no electric field inside, right? What was the assumption for that?
It's closed.
What's that? Under electrostatic conditions. We no longer have electrostatic conditions. The charges are allowed to move. Because the charges are allowed to move, we can now have an electric field within the wire. So, because we are moving, the electrons feel. They don't really feel. They respond to the electric field, and the valence electrons will move in that direction, bouncing along. Okay, and they start to jiggle. The electrons are hitting them. Not the electrons. The electrons are hitting the atoms, and the atoms start to jiggle. Just a little. They jiggle it just a little bit. Okay. Anyways, that's. I guess you guys don't know that song. So the electron. No, I'm not going to sing it. At least not while the camera's running. So the electrons hit the atoms. The electrons hit the atoms, and the atoms start to move. Well, what happens when atoms increase their movement? Their temperature starts to increase. This is why when you are using electrons, using electronics, that they get warm. This is why if you have your laptop on your lap and you're using your laptop a lot, it gets warm on your lap. It's not because it's trapping your thermal heat of your body. No. Okay? This is why if you're playing a video game on your phone and you touch the back of it, okay, like a really intense video game, like some of the ones I have on my phone, okay? XCOM. Okay, if you've got the real if you have the real 3D game that you spin around, it has 3D animation, that sort of stuff. You're working the video processor on your phone like crazy, and it will get really freaking hot. Okay, hot to the touch, like ouch, hot. It's because there's a lot of heat giving off from the electrons hitting the atoms. There's a lot of electricity flow. Okay, the best conductors, then, because here's our wire. We're looking for good conductors here. The best conductors allow the freest flow of electrons. I think there's 3 E's in that. Otherwise, it's freest or freest, but we want the freest. The freest flow of electrons. Okay. Now, gold is an amazing conductor. It's a terrific conductor. It's also hella expensive. Okay. So we have found another option that it's maybe not as good a conductor, but it's a very good, and it's a heck of a lot cheaper. Okay, and it's copper. Okay, so copper is really what we tend to use in our wires. However, it's not cheap, and that's why you hear a lot of you may hear of copper burglary, or copper wiring getting stolen from construction projects, because it's worth a fair amount of money. You can still melt it down and get a fair amount of money for the copper metal itself. Okay. Do want you guys to remember. Okay, the current. Current is the flow of positive Q. It is the flow of positive charge. Okay, electrons, well, they move a little. It's the flow. Remember, it's the flow of the charge. But electrons are really small. You just need a lot of them, right? Okay, so in fact, you guys have a problem in your book that's gonna illustrate this. So we have another wire here. Okay. Okay, and we have a distance x. Okay, we have our electric field flowing through the wire, and what we're going to try and find is the current through the wire. And here's the technical equation for current. It equals delta Q over delta T. Okay, but now work with me here. This is going to equal N, okay, where N is the number of charges, okay, or the number of charge-carrying particles per volume, okay, times the volume, times the charge of an electron. So the charge-carrying particles are going to be the electrons. Then we'll multiply this by the charge of electrons, divided by our delta T. So work with me here. This N is how many electrons there are in a given volume. That's the volume of your space right here. Okay, and QE is the charge of your electron. So really, this is your total charge right here. Yeah.
Isn't N low?
You can be, yeah, but we're kind of calling it something different here. Okay. Now, this volume here, if this circle right here is cross section A, if it has cross section A, and this is our distance delta x, then this volume becomes N A delta x Q, right? Q on electron divided by delta T. Does that make sense?
Yes.
Okay. So we're going to rearrange this, and I'm going to write our current as I equals N A Q. And then what do we have here? What does that look like?
Velocity.
Delta x over delta t is a velocity, right?
Ooh.
Okay. This is called, it's a velocity, it's called v sub d, and it is called the drift velocity.
Wait, is that root?
It's a v.
Oh. What is the
N is essentially the number of it's the number of electrons in this given volume. Okay, and then here's the charges on the electrons. Yes. Q VD V sub D drift velocity. All right. Okay, now you're going to solve for drift velocity in one of your problems, and we'll actually go over it tomorrow. Because it's, again, you'll be surprised at how little the drift velocity is. But I want you to think of current like this. Your garden hose at home, okay, whether you believe it or not, okay, is already sitting there filled with water, usually. It's filled with water, right? You have water in your hose. Okay, to the point where if you turn on the hose, do you have to wait forever? Okay, some hoses do. I used to have a hose that we would just have to wait there for a good 15, 20 seconds before the water comes flowing through. Okay, but most hoses, okay, particularly if you have like a nozzle on the front, okay, if you have a nozzle on the front, okay, you've got water all the way up to the front of the hose. You turn on the water, and what happens to the water? Instantly, it's shooting out. That's the idea of current. You have electrons throughout your wire, throughout your circuit. The electric field turns on. Okay, you allow your potential, okay, your battery, whatever it is that is driving your electrons, you connect the circuit, and that pushes and creates the electric field that accelerates the electrons. The electrons themselves don't necessarily move very fast. However, the amount of charge that you have going through does move. And it's because the field, it's the force that pushes everything through. In fact, the water, I believe, is at the speed of sound that shoots through the hose.
What?
The pressure wave that shoots through it travels through the water at the speed of sound in water. And so that you turn, if you got water right there and you turn on the hose, that quickly is the response time between the whole 200 feet of your hose outshoots the water. All right, that's why you don't have to wait that long.
Is that
Question.
why we perceive it as being so fast? Is because we think it's empty, and then the electrons shoot through like the battery almost, but they're already sitting in the wire. Basically, is that what you're saying?
Is why we perceive it to be so fast?
Yeah.
Yes.
Okay.
The analogy is the same. Yeah, the water shoots out almost instantaneously. Same thing as,
Not just that. It's only not fast.
right,
Okay.
right.
So if we turn on our phone, are we turning on the electric field?
You are allowing the electric field to flow through all of your electronics in your phone.
If we turn on the
When you turn it on, okay, you turn on the switch that allows all these things through. Now, you have various switches within your phone. I think those are the transistors, the little mini switches that allow various things to happen within your phone. And when we get to integrated circuits, and then it's then the logic, then you start getting logic cards, and all the logic is, and your CPUs are really, 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 really tiny transistors, which are tiny switches that are turning everything on and off. And so they become, that's where the binary, the ones and zeros are really on and off for that particular. Okay, and so we have a switch, but that's really a bit. And whether are you using that circuit or are you not using the circuit, and on the tiny scale, that becomes memory or it becomes other logic purposes. Okay. Okay. Oh no, I lied. Simon wasn't. Ampere. I don't. Simon was Ohm's name. So, anyways, okay, we have a length here. I'm going to give you guys J. This is the silly way of defining resistance, by the way. We moved on to resistance. We have J, which equals our current divided by our area. Okay, and this is called our current density. I don't know why it's J. Okay, but we know it's our current. Our current, as we defined up here, was NA Q VD, right? And we're dividing that by A, then those go away. And this becomes, okay, let me make sure I'm doing this right. Okay, this becomes, this is our charge density. And Ohm said, okay, he said that charge density is proportional to electric field strength. Okay, charge density is proportional to electric field strength. All right, and he defined it in terms of this. That J equals sigma, not the same sigma as before. He called it sigma. He called this conductivity. Okay, which is a function of the material times the electric field. All right? You follow me so far? Right. Oh boy, that's right. I guess we got to get out of here today. Okay. All right. So I think we can get through this real quick. Okay. So this is not very practical. This is not a practical way of explaining this. What is more practical is this: that we have our voltage. Okay. Our voltage is equal to. Okay. In this thing, it's going to be equal to. I'm sorry, the voltage difference between this point and this point, okay, is going to be equal to the electric field through there times that distance, right? Yeah. Right? V equals, the potential equals ED, right? So if we have a field through here, and we have a change in our distance, then the electric field times that distance is going to give you our change in voltage. Okay, we can write this as E equals delta V over L. All right, so we're going to take this and plug it in here, and we get J equals sigma delta V over L. Okay, and this equals this up here. You follow? This is good. This is just going to be a whole bunch of algebra manipulation here. So hang with me here. Okay. If these two things are equal to each other, then we get, what's that? Okay. Okay, well, you guys need to go back and watch the film. Okay. Oh, delta V. Guys, tune in. If we solve for our voltage, it's going to equal IL over our area times the sigma. Well, 1 over sigma, sigma is conductivity. We define 1 over sigma is resistivity, because it's the inverse of conductivity. Okay, how much it resists rather than how much it conducts. All right, so, and this is rho. Okay, which is why I didn't want to call the charge density, the volume density of charge, rho. I didn't want to call it that, because we have a rho that's coming up here. Okay, because of this, that's going to plug in here, and this becomes our voltage equals rho times the length over the area times the current. This value right here, rho L over A, is called our resistance. It is equal to capital R. And so now all of a sudden we have Ohm's law. If we go back this way with it, is that our voltage equals our current times our resistance. And that's Ohm's law. The unit for resistance is called an ohm. Okay, and because we would use O as the variable, but if you write 20 ohms, all of a sudden it looks like 200, and there's ambiguity there. So instead of using O, we use the Greek letter for O, which is an omega. And this is, okay, and this is equal to a volt per amp. And that's our resistance, and we'll get into, that is enough for today.